So in this video, we'll try to explain the use of the moody diagram. This diagram, its main purpose is to obtain the Darcy friction factor, which is right here on the left. And using the information about the Reynolds number and the relative pipe roughness that you have. And well, first we have four different regions here: the laminar flow region, the transition region, the this is the turbulent region, but it doesn't have the it doesn't have it. So this part here, this is the turbulent region, and this is the completely turbulent region in the right. First, we're gonna start with the laminar flow. Well, first of all, we need to parts of information here: the Reynolds number and the relative pipe roughness. The Reynolds number, you need to get it from this formula, which is the liquid density times the velocity times the diameter over the viscosity coefficient. And the relative pipe roughness is the material roughness over the diameter. The roughness, you can get it from tables like the one we have here on the left. You look for the one that you're using. For, like, for example, if you're using a PVC, you use this number. Glass, plastic, and perspex. You have a 0.0025 epsilon number, and you divide that over the diameter, and you get the relative pipe roughness. So once you have those two numbers, first of all, if the Reynolds number is too small, you'll be in the laminar region, and there's a straight formula to calculate the Darcy factor, which is 64 over the Reynolds number, and that would be your F value straight up. Now in the transition region, you usually don't calculate things here. Okay, so in this part, we barely anytime calculate the friction factor in that region, because it's a small region and we don't usually have fluids flowing through it. Plus, it's kind of a stretch. The way that works, it's like not really an definite range from laminar to turbulent, and the transition region is kind of a blurry thing. So we will go straight to the turbulent region, which is this one right here. So assuming you have a material, like, for example, you have a Reynolds number of 3 million. I'm not gonna do it because it's gonna take a while. But you have a Reynolds number of 3 million. So you get here to the 10 to the 6th. You count 1, 2, 3, 4, 5. So yeah, it's 10 here. So you count to the third one and you're here. Now, assume you have a smooth pipe, like for example, a PVC, because you got this 0.0025, and you divide that times the diameter, which let's say a 40 millimeter diameter, and you get, I'm taking the calculations here, you get a value of 6 times 10 to the minus 5, which is gonna be this, no, sorry, it's gonna be the one over that one. It's gonna be around here. Yeah, so now you use this line and you start going up on it until you get to this desired part, which is 3 times 10 to the 6th, and the point where it makes the intersection, that's the one that we're interested in. We can see that it's practically in this line here, and if we follow it to the left, it's gonna be this one. And we got 0.01, 2, 3, 4, 5. So this is gonna be 0.011. 1, 1, and that is gonna be our, sorry, that is gonna be our Darcy friction factor. And now, as we increase the velocity in the pipe, we are gonna also make it more turbulent, and we can get to the completely turbulent region. So let's assume that we change our Reynolds number to 10 to the 7, like let's say here 2 times 10 to the 7. And we got a relative pipe roughness of 0.002. Like, I don't know, like you're using steel pipe with the diameter that gives you this number. And you follow this through here. As you can see, this is practically straight line. From here, they are all practically straight lines. So yeah, the Reynolds number is not gonna affect that much on this part, because once you get to the completely turbulent region, it behaves in a like a constant. So you have this 0.002, but it is important to mention that if you have a low Reynolds number, like for example this 0.002, and if you have a Reynolds number of 10 to the 5, then you will still be in the turbulent region, but not completely turbulent. So you will have to follow the line. But here, it's a straight line, so you follow it all the way through here. And it's gonna be 0.02, 1, 2, 0.022, no, 0.024, because this line is, yeah, each one is 0.002. So you will get this 0.024. Doesn't look good, but it's the spirit that matters. So that's pretty much how you use the moody diagram, and you use it to calculate the Darcy factor, which you use then to calculate the head losses in a pipe. And that's pretty much it.